Week 14, Part 3, Multiple Slits and Diffraction Gratings. So what happens when we have a whole bunch of slits, more than just two? What happens with 3 or 4 or 500 or whatever? Let's take a look at that case. So here is a calculation. Let's start with 2. That's what we've been working with before. With just 2 slits, what you're seeing here is the intensity pattern on the screen. It has these maxima and minima that go back and forth, and it generally drops off a little bit as you go away from the center line. That's something we'll talk about later on. But the main thing is it just smoothly goes back and forth between these maxima and minima when you have 2 slits. If you have instead 3 slits, a funny thing happens. You get an extra little bump in between those maxima. The other thing to notice is that the peaks are at the same places. The angles didn't change at all. That's important to remember. Now this is assuming that you've got 3 slits in which the separation from one slit to the next is the same as when you had 2 slits. So as long as the separation from one slit to the next is kept the same, then you get sort of the same peaks. And that does make sense. If you go back to the diagram, maybe I should try to do that here. Let's go back to this diagram and explain why that is true. So stop and share. And I've got to change cameras. Here we are. If you think about if you're at a position at an angle where there is a maximum with 2 slits, where these two end up that the phase shift here is exactly one wavelength at this particular angle. Do you see that if I were to open up another slit down here the same distance away, it would again have that same phase lag with the previous one, and it would have a phase lag of twice that for the first one. So they would all still just be in phase. As long as you keep adding slits that same distance apart, when they're in phase one to the next, then the following ones are also in phase. So the angles for the maxima stay exactly the same. What isn't as simple to explain, and in fact I'm not really going to explain it, is what happens when you're not right on the maxima. And so here we would have expected a minimum down where the 2 slits were canceling each other out. They were exactly half a wavelength off, but then now you've got a 3rd slit, and so it's got some intensity still there. And so you get a little bump from that. When you go up to more slits, you get more bumps, basically. That's how it works. So you still have these same maxima. Notice that they don't change their positions at all. They stay at exactly the same angle. So the formula we've been using to calculate where these maxima are is true for more than just 2 slits. It works for any number of slits. But the sort of shape of the curve has changed rather dramatically. Notice as I go to increased numbers, you get more and more of these little bumps down here. It's actually n-2. So here are 9 peaks, and if you count up, there should be 7 little bumps in between. So you get more of those little bumps. The other thing to notice is that the main peaks are getting narrower. As you add more and more slits, the main peaks get progressively narrower and sharper and sharper and sharper. So when we get up to 20, they get very narrow. And one can, in fact, produce these things in such a way that you have the equivalent of hundreds or even thousands of slits, in which case these become very narrow lines indeed. So one other thing to note is about the height of the peaks. I've normalized everything to 1 here. Certainly if you add more and more slits, all other things being exactly the same, you would expect to get more and more intensity here. I've just taken that factor out so that we can more easily compare things. Now, in the case where you go to hundreds or even thousands of slits. They don't really even end up being slits anymore. They're called simply lines. And so let me switch back to my camera view here to show you an example of what's called a diffraction grating. This is a diffraction grating, and oddly, it doesn't look like it does much. There's not much going on there. You would think this was just a slide with a piece of plastic on it, except if you look carefully, every now and then you see some colors in there, and you wonder what that's about. Maybe that's a little hard to see here. Let's see if I can make them show up a little bit more here. If I can get this thing to be a bright white, then hold this over it. Now you're starting to see some colors, some funny bands of color on either side of that bright white part there. Do you see those colors show up? So what's going on there is essentially that we're kind of using it backwards here, but I've got a bright light shining, a bright object here shining through this, and then it produces these peaks. I want to show you just another way of doing the same thing. So I'm going to use my cell phone as a light. And what I've got here, now actually let me show you a diagram of what I'm about to do first. Got a nice diagram here, might as well show it to you. So here is an example of what you can do with a diffraction grating. So now this diffraction grating, you could imagine, has thousands of slits in it, very, very tiny slits. In actual fact, the way they are made is by simply scoring the surface to sort of rule the surface with these little lines, they call them. And they function as if there were just a whole bunch of little tiny slits. And that has the effect then of when you put light through it, why you get, again, these maxima at particular angles. Let's look at the straight through direction. We'll get a real nice bright line here. Just focus on this center ray right here. We'll get a nice bright line there. Off at some angle from that, we'll get another maximum, and then out still further would be another maximum. This would be m equals 1 perhaps, and m equals 2 would be up here that I haven't shown. Down here is m equals minus 1. So that's just from the light passing through here, shifting off to these other directions. And remember, when you have a whole lot of these slits, it's not a smooth function. It's a very sharp function. So you have a very narrow line here. And over here, similarly, a narrow line, except that it gets spread out, because what I'm describing here is when the source has a bunch of different colors, which means different wavelengths. And the formula we're using depends on wavelength. And so the angle that comes out depends on wavelength, and that's why it spreads things into this spectrum. Now the lens here is simply showing if you have a lens so that the light without the grating would have been focused to a nice sharp point here. Then essentially each of these gets shifted, and you end up focusing the spectrum that you get also gets nicely focused into, so that all of the red rays come to one spot here and all the blue rays come to one spot there. At each of these lines where the ray comes in at a little bit of an angle, then it gets deviated by that same angle we calculate using n lambda equals d sine theta. It's that same angle here as it is down here. But this is the way you can create a nice spectrum. Diffraction gratings are often used in this way, so that if you're trying to see what colors are present in a light, pass it through a diffraction grating, use a lens to focus it nice and sharply, and you'll get a beautiful spectrum like this. Now this, of course, is just a drawing of it. It's not real, but I can do something kind of like this using my cell phone as the light source. And so here's my cell phone Nice bright light source, and that's shining on a lens here. And now if I can find what I did with the grating, here it is. I'm going to tip this whole thing up, and you see it's created a nice bright spot there. It's not quite in perfect focus. Let's see if I can get it a little bit more in focus. No, it looks like I can't. Here we go. That's a little bit brighter. Got a nice bright image there. And you can see that. And now if I put it here, there, you see the spectra on either side. I'm just putting the diffraction grating into the beam, and you get that spectrum on each side. I don't actually have to hold it that far away. And especially if I turn some of the lights off, you'll see it even better. So now as I get still closer, you can start to see a second, oh, barely, just barely, you can start to see a little bit of the second order. That's the N. Yeah, it's not in focus anymore. But do you see just a little bit, a hint of the second order spectrum that's coming into play there? Let's see if I can get this to work better. Further away. There we are. My light turned off. Well, we'll quit. So what that was showing you was the first and second order. Now let's do a little calculation. Let's do an example for gratings. First thing to remember is that gratings are often not given, they don't tell you the spacing from one line to the next. What they will often say, in fact this one says on it right here, that it's 500 lines per millimeter. And let's imagine that I put the screen 15 centimeters away. And what I'd like to know is how far from the center will the middle of the spectrum be? So where we had that bright spot in the middle, and then off to the side was one of the spectra. I'd like to know how far away is that going to be to the middle of that spectrum. And we'll talk about the first order spectrum. That's the only one we could see very well. And then later we could ask, well, how far apart are the blue and the red ends of the spectrum, sort of guessing that those might be at 400 and 700 nanometers. Those are numbers that are often used for the limits of vision, human vision. So how do we do this? What do we do with this 500 lines per millimeter? Well, so here's a picture of what's going on. So I've got the lens and the grating, and I'm trying to get this angle here, the angle between the straight through direction where we had just a real bright spot, and then over here is where we had the spectrum with the colors. And I'd like to know what's that distance there, knowing that this was about 15 centimeters away. First of all, what do we use for D? D is just 1 over this number that's on the slide. When it says 500 lines per millimeter, we'll just put that over. How many millimeters per line? It would be 1/500th of a millimeter from one line to the next, or 2,000ths, if you like, 0.002 millimeters, which is 2 times 10 to the minus 6 meters. Then remember our formula, n lambda is d sine theta. This was the 2-slit formula, but it works for any number of slits. That doesn't matter at all. Telling you where are these maxima. So this is going to be the m equals 1. Here is m equals 0. Down here, m equals minus 1, and we won't go beyond those for now. So here's the calculation. I just turned this around to solve for theta, trying to get this theta first. So if theta is the arcsine of n times lambda divided by d, n in this case is going to be 1. And lambda, well, we'll just take the middle of the spectrum. If blue to red is 400 to 700, the middle of that is 550. So let's calculate it that way. And 550 times 10 to the minus 9 divided by d. D is the slit, the slit spacing, if you like. So that's 2 times 10 to the minus 6 meters. You do that calculation, you get about 16 degrees, which looks kind of reasonable given what I was doing. Um, Notice, once again, here we had fairly substantial angles. These things were out quite some distance apart. That's because the slits were so very close together. 2 times 10 to the minus, I mean, 2 thousandths of a millimeter. That's really close together. That's 2 microns. I'm trying to think what that would be in the size of a human hair. I think a human hair is usually about 20 microns, so this is even quite a bit smaller than a human hair. So anyhow, out comes this 16 degrees. That doesn't tell us this distance, y, we could call it. So how do you get y? Well, you draw this triangle out here again and try to get y, knowing this is 15 centimeters. And that's just using a tangent. The tangent of this 16 degrees is what this angle is in here. The tangent of 16 degrees is y over 15, and so y is 15 times the tangent of 16, and that comes out to be 4.3 centimeters. So not quite 2 inches is how far apart it was, and that's where the spectrum would have been when I held the grating right up to the lens and it was 15 centimeters away. Later on, I was holding it much closer. What about red and blue? Well, that's pretty simple. For red and blue, we simply do the calculation again with different wavelength numbers in here and get a different angle. Then you'd have to go through this and get a different Y position and do that for both red and then for blue. And you'd find these 2 different Y positions for red and for blue. And then you subtract the 2 to get the distance between them, which would tell you sort of the size of the spectrum. And that's 2.54 centimeters, happens to be about exactly 1 inch. So that's an example of how to work with gratings, which are essentially multiple slits.